Today we're going to be talking about graphing cube root functions. So first we're going to talk about square root functions, which is what we did in our last lesson. So we'll review that just briefly because a lot of the things we did for that apply to cube root functions. Then I'll introduce the parent cube root function, which is just y equals the cube root of x. We'll find some points on it, which will help us as we move forward. And then we're going to talk about applying transformations. So we're going to be stretching this and moving it around, which will change its position or size on the graph. The basic shape is going to stay the same. We're just going to transform it uh, around on the xy plane. So a square root function for my first example. Now this is a review because we did these already. But my first example, I'm going to use the square root of x minus 4 plus 1. The most important feature of the square root function is the endpoint, because the square root function comes to a stop at a particular point. In order to figure out the endpoint, which is the same skill we're going to use in cube root functions, you take the number being added or subtracted on the inside, but you need its opposite, because what you really want to do is figure out when the square root is 0. So in this case, I see a negative 4 here. So if I want to get that 0, I have to stick in positive 4. So that's the x value for my endpoint. And then the outside number will determine the y value. It's not backwards though. That's just how far the graph has been moved up. So I'm going to change the sign for the inside one to find the x. But the outside one, I don't change the sign. It's just 1. So my endpoint for this particular square root function is 4, 1. And I'll put it right there. Now, most of the time, square root functions go to the right. This one is no exception. So if I want to find a couple of more points, I need to stick them in order to find them, 4, 1 being my endpoint, which I already found. Easiest is to make the inside a square. So if I want the inside to be 1, I have to stick in a point that's 1 bigger, 5, which will give me the square root of 5 minus 4, which is 1. But the square root of 1 is 1, so I get a total of 2. The next nice square, because the square is 1 squared is 1, 2 squared is 4, 3 squared is 9. So next I want to try to make the inside 4. To do that, I would have to stick in 8, which might actually be too far over for the graph I've drawn. But I'm going to find the point anyway. The square root of 8 minus 4 is 4. So that's 2 plus 1, which is 3. Notice my y's count up by 1s, because if I do each square in a row, these go up by 1s. So the next one is 5, 2, 6, 7, 8, 1, 2, 3, 8, 3. So a few points will give me the curvature a little better. These all have the same basic shape. You've got an endpoint. It's a half a parabola on its side. So I go through my points and I have a nice curve. These ones have restricted domains. X has to be greater than or equal to 0 because you can't use a negative inside a square root. And the range will always depend on the endpoint. I'm sorry, X has to be greater than or equal to 4 because I'm subtracting 4. It needs to be bigger than 0. Use the endpoint to find the value for the domain. So x is greater than or equal to 4 in this case, and then the range is based on the y's. The smallest y on this graph is 1. Since I'm going up, the rest of the y's are bigger than 1. So these ones have a domain and range that's restricted based on the endpoint because the graph just stops there. When we move to cube root functions, they actually don't stop. They do have a point in the middle. I call it a vertex. You can also refer to it in cube root functions as a point of inflection, which is where the curvature of the graph changes. But I'll be referring to it as a vertex. So the basic cube root function has its vertex at 0, 0. There's nothing being added on the inside or on the outside. So 0, 0 is the vertex, the central point. Now the cube root function is going to curve up and over, just like the square root function, although it's going to be a little steeper right at the beginning and flatter on the end. So we're going to find a few points. So if we think about cubes, 1 cubed is 1. 2 cubed, though, is 8, because that's 2 times 2 times 2. And 3 cubed is 27. So these get bigger much faster than the squares do. But I mean, it's the same sort of relationship. It's just because it's cubed instead of squared, it's more extreme. So if you think about this, then 1 cubed is 1. So if I do the cube root of 1, I'll get 1. And the next nice point will be the cube root of 8, which is 2. And then the cube root of 27 is 3. They get even crazier from there. There's no way I'm going to fit to 27 on here unless I go by like 5s. I am going to go by 2s on my x-axis, which puts 8 right here. So I've got 1, 1 and 8, 2. So even if this one goes up like that, it flattens out pretty significantly. Now, the other big difference between the cube root function and the square root function is that you can take the cube root of a negative number. Because you're doing multiplying 3 times, if you cube a negative number, like -1 cubed, -1 times -1 is +1. When you multiply again, it becomes negative. So you can take the cube root of a negative number. Square roots, the square root of a negative number is not real. You don't get a real answer. But cube roots do. So you can actually use negative numbers as easily as positive numbers in a cube root function. They are symmetric because then all the negative sign does is bounce back and forth. 2, 4, 6, -8. So -8, -2. The next point would be -27, -3, which I said already, I don't really have room to draw. So the cube root function has the same similar shape to the square root function, but you'll note that in the it goes both ways. It has a part going up and to the right and a part going down and to the left. So make sure you draw both. As far as the domain and range, that means the domain is all real numbers. And the range also all real numbers because it goes both up and down. So unlike the square root function that has a domain that doesn't include all real numbers, the cube root function's domains always include all real numbers and the range, also all real numbers. So this is your basic parent function, and all other cube root functions you can consider to be transformations of this function. In the same way we did with the square roots, we're going to move it around. We might stretch it or flip it upside down. But all of our cube root functions are transformations of this parent function. So we're going to do a couple examples involving these transformations just to give you an idea for what we're doing, and then you can practice on your own. So my next example, square root of x plus 2, or sorry, cube root of the quantity x plus 2 minus 3. So looking at this one, I can tell you already where the midpoint, the vertex, or the point of inflection will be. Remember, the number on the inside is going to be backwards because I'm trying to make the inside 0. So that's -2. But the one on the outside I don't change, so I leave that as negative. So -2, -3, that's the vertex. The central point here has been moved 2 spaces to the left and 3 spaces down. It's down here now. Since there's no a being multiplied in front, you can actually, if you learn this spacing, you can use the same spacing here if that's what you want to do. Or you can use an XY chart, which I think for most of you is probably going to be your preference. So if you think about it, we've got our first point, -2, -3. I'm going to start by sticking a point 1 bigger in here, -1, in order to make it a cube root of 1. So if I stick in -1, that gives me the cube root of 1 minus 3. But the cube root of 1 is 1, so I get -2. -1, -2. The next nice cube root will be 8. In order to get 8 in there, I have to stick in 6. 6 plus 2 is 8, so that's the cube root of 8 minus 3. The cube root of 8 is 2, which makes that 6, -1, which is way over here on top of my little XY chart. So see, these get really far over. You may not have room on your graph to fit more than one of these whole number points. So just do the curvature as best you can. And then remember, the graph is symmetric. So on the other side, once you have points on one side, you can actually just copy them over to the other side of the vertex. So that was 1 up and 1 over. This one, though, is 8 over and 2 up. 2, 3, 4, 5, 6, 7, 8. Down 2. So there's the symmetric point there on the other side. You could stick in x's to find them. I mean, this one is -3, which if you stick in, it'll give you the cube root of -1, which is -1 minus 3 is -4, which is this point here, -3, -4. And this one will be -10, -5. Yeah. So you can stick them in to an XY chart if you prefer. I tend to use the symmetry just because it is easier, faster. And there's my cube root function. And if you have to name the domain and range, domain is all real numbers, range also all real numbers. I'm going to do one more of these, something with an A, just so you can see how that works, probably upside down too. So let's go with -3 times the cube root of x plus 5 plus 2. Let me move this over a little bit. So looking here at the transformation, it's going to be 5 spaces to the left. Remember, inside's backwards, so I have to use -5 for that. And don't change the outside, so that's +2. -5, +2. That's my vertex, my central point here. For points nearby, it's easiest if I go up 1. So the next point I'm going to try is going to be -4, which gives me the cube root of 1, which is 1. But now I'm multiplying by -3, so that's -3 plus 2, which is -1. -3 plus 2, yeah, that's right. So -4 is down here at -1. So that's much steeper. This is well, I want to say taller, but no, it's going down. But my middle is going to be a lot steeper than it was in my previous example, because when I multiply by 3 out front, it stretches the graph vertically. The negative sign is going to make it upside down, which is why this is going to go down instead of up. If I wanted another point, I'd want to make the inside 8, which means I'd do +3. When I do that, I get the cube root of 8, which is 2. So this is -6 plus 2, which is -4, which is right there. So that'll give me my curvature pretty nicely, like so. Just using the symmetry of the situation, this point will be right here. And 8, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6. This one was 6 below and 8 to the right. So this one is 8 to the left and 6 above. So the other half looks like this. And there's my cube root function. Notice quite a bit taller than this one because I multiplied it by 3 and also upside down. If somebody asks you for the domain and range, they're both all real numbers. That gets a little bit boring for cube root functions because they're always both all real numbers. Just remember to distinguish them from square root functions that have restricted domains. And that's it. You can get started on your work.